Welcome to the Deep Dive. Today, we're going to be exploring something pretty interesting. It's called Trading Inference-Time Compute for Adversarial Robustness. It's a research paper, and it tackles a really crucial challenge in AI safety, and that's protecting those large language models, LLMs, from adversarial attacks. So we've got this research paper as our main source today, and we're going to unpack the key findings, the implications, and even some of those really interesting attack strategies that they investigate in the paper. Because, as LLMs are used more and more in real-world applications, from like browsing the web to executing code, their vulnerability to these adversarial attacks, it just becomes a serious concern.
Absolutely. These attacks, they can have some really significant consequences, potentially allowing, those malicious actors to manipulate the LLMs for their own harmful purposes. And what makes this paper, particularly interesting is its focus on inference-time compute as a potential defense mechanism.
Okay, so let's kind of start with the basics. Can you explain what these adversarial attacks are and why they pose such a significant risk, especially with these increasingly powerful LLMs?
Yeah, so an adversarial attack, it's basically a way to trick an LLM by manipulating the input it receives. So it forces the LLM to produce that specific output that the attacker wants. So imagine you have an LLM that helps you browse the web. An attacker could craft a malicious website prompt, and that could inject code to steal your information.
Oh, wow. So instead of attacking the model's code or its training data, they're actually exploiting how it processes information.
Exactly. The attacker's really exploiting the model's inherent vulnerabilities and how it interprets and responds to input.
And the paper suggests that increasing that thinking time given to an LLM at inference time could actually make it more robust to these attacks. Can you maybe elaborate on this approach a little bit and how it differs from the more traditional adversarial training methods?
Sure. So those traditional methods, like adversarial training, they involve exposing the model to various attacks during training. But this is really computationally expensive, and it requires you to anticipate those specific attack types, beforehand. But this new approach explores scaling that inference time compute. So you're giving the model more time to process and reason before it responds. So the idea is that this increased processing time might allow the model to kind of detect inconsistencies or potential manipulation attempts in that input, making it less susceptible to those adversarial tricks.
So instead of trying to preemptively train for every possible attack scenario, we're giving the model more resources to analyze and critically evaluate that input that it receives.
Precisely. It's kind of like giving the LLM a chance to think twice before it acts and allowing it to potentially recognize and avoid those adversarial traps.
And the paper, it tested this theory, right, across various attack types and tasks. Could you maybe walk us through some of the key findings and those different types of attacks that they investigated?
Sure. They looked at things like mathematical tasks, policy violation scenarios like the strong reject benchmark, and misuse prompts. They also looked at website prompt injection using AdVSimple QA, and even image classification attacks. And even, they went as far as attacks designed by human red teamers. And what they found was that increasing that inference time generally improved the robustness of reasoning LLMs. So it led to a decrease in the success rate of those attacks across a variety of those tasks.
Okay, that's a pretty diverse range of attacks and tasks. Can you give us maybe a specific example of one of the attacks and how that increasing inference time led to improved robustness?
Yeah, so one intriguing finding was that the models showed improved resistance to many-shot jailbreaking attacks on mathematical tasks as that inference time increased. So in many-shot jailbreaking, the attacker provides multiple examples of successful attacks, and they're attempting to kind of teach the model to bypass its safety constraints. And the study found that with that increased inference time, the models were better able to kind of recognize that pattern of malicious intent in those examples and avoid falling for that jailbreak.
So that increased thinking time allowed the model to recognize the manipulative nature of those many-shot prompts and really just adhere to its safety guidelines.
Exactly. It's as if the model, with more time to process that information, was able to kind of step back, see the bigger picture, recognize that adversarial nature of the prompts, rather than simply mimicking those provided examples.
That's really fascinating. It suggests that increased inference time might help LLMs develop more nuanced understanding of the input they receive, so they're less susceptible to manipulation.
That's definitely a key takeaway from this research. It suggests that the relationship between that inference time and robustness is more complex than just, more time equals more safety. It's really about how effectively the model utilizes that time to analyze and reason about that input.
Now that we've kind of established those potential benefits of that increased inference time, let's explore some of the challenges and attack strategies that the paper uncovered. You mentioned this think less attack earlier. Could you explain what that is and why it's particularly challenging for reasoning models?
Yeah, so the think less attack, it's a very clever strategy where the adversary aims to trick the model into using less compute time than it would normally use. And the goal isn't really to directly force a specific output. It's to make the model overconfident and rush to a conclusion, thereby increasing its vulnerability to other types of attacks.
Oh, so it's like the attacker is trying to lull the model into this false sense of security by presenting the task as deceptively simple?
Exactly. The attacker might craft a prompt that appears straightforward on the surface and cause the model to kind of prematurely terminate its reasoning process and arrive at a less informed and potentially incorrect conclusion. For example, they might use ambiguous wording or like cleverly structured prompts to trigger a less computationally intensive pathway in the model's decision-making process.
This think less attack seems particularly insidious, just because it directly undermines that core principle of using increased inference time for enhanced robustness.
Right, it highlights the fact that simply increasing that compute time isn't a guaranteed solution. We need to ensure that the model is actually using that time effectively and not being tricked into cutting corners.
Yeah, and the paper also talks about another really fascinating attack vector called nerd sniping. Can you describe how that attack works and why it complicates that relationship between inference time and robustness?
So nerd sniping refers to the strategy of exploiting the model's tendency to get stuck in unproductive reasoning loops. The attacker crafts a prompt that triggers a computationally intensive but ultimately pointless line of thought. So essentially distracting the model from the actual task and wasting all those precious compute resources.
So it's kind of like leading the model down a rabbit hole of its own making, causing it to expend all of its energy on like irrelevant or circular reasoning.
Yeah, that's a great analogy. Like imagine giving the model a riddle. That leads to an infinite loop of calculations or a logical paradox. And the model, driven by its programming, to thoroughly analyze that input, might get trapped in this loop. And it prevents it from arriving at the correct answer or even adhering to its safety guidelines.
Yeah, these attack strategies like think less and nerd sniping, they seem to suggest that we need more sophisticated methods to guide that model's reasoning process and ensure that it's focusing its computational power effectively.
Absolutely. Robustness isn't simply a matter of raw computational power. It requires mechanisms that help the model allocate its resources wisely, recognize that manipulative intent, and avoid falling into those adversarial traps. The paper really highlights the importance of considering the quality and the efficiency of the model's reasoning process, not just the quantity of computation.
Now, the paper goes into some very technical details about their experimental setup, including the specific tasks and attack methods they used. Can you give our listeners a brief overview of those details?
Sure. As we discussed, they tested a variety of tasks, ranging from solving those math problems to adhering to safety policies in different scenarios, and to challenge those models. They used some pretty sophisticated attack techniques, like that many-shot jailbreaking, which involves providing numerous examples of those successful attacks to influence the model's behavior. They also utilized soft token attacks, which involve directly manipulating the model's internal representations of language.
Could you explain what you mean by those internal representations, for those who might not be familiar, with the technicalities of LLMs?
Sure. So imagine an LLM as like this complex network of interconnected nodes, each representing a different aspect of language. And these nodes form a sort of mental map of language within the model. And those soft token attacks target those internal representations by subtly altering the activation patterns of those nodes. So it influences how the model interprets and processes language without actually changing the words in the input.
So it's like manipulating the model's understanding of language at a deeper level, almost like planting subliminal messages within its thought process.
That's a good way to think about it. Those attacks are particularly challenging to defend against because they target those underlying mechanics of how the model processes information rather than that surface level input itself.
These attack techniques definitely paint a picture of the complex landscape of LLM security. So what were some of the key conclusions that the researchers drew from their experiments?
Well, their main takeaway was that scaling inference-time compute holds a lot of promise for improving that LLM robustness, particularly against those clearly defined tasks and unambiguous safety policies. However, they also emphasize that it's not like a cure-all, and it must be combined with other robust defenses, especially when dealing with those ambiguous tasks or sophisticated attack strategies like that think less and nerd sniping.
So while increasing inference time can really bolster those LLM defenses, it's crucial to recognize its limitations and develop those comprehensive security strategies that address those nuanced ways that these models can be manipulated. Okay, so we've really explored the potential of scaling this inference time to enhance that LLM robustness. But we've also uncovered some of the challenges, the attack strategies. That makes this a pretty complex problem. So as we kind of move toward these more advanced and capable LLM-powered systems, what practical steps can we actually take to ensure the security and the reliability in real-world applications?
Well, while the paper doesn't necessarily offer concrete solutions, it does point towards some really important considerations for building these more robust LLMs. One key takeaway is that need to kind of shift our focus from simply measuring robustness in terms of those computational resources to actually evaluating the quality and the effectiveness of the model's reasoning process. It's not just about how much the model thinks, it's about how well it thinks.
So how do we move beyond just increasing that compute time and start focusing on improving the way these LLMs reason? Are there specific approaches or techniques that you find promising in this area?
Yeah. One area of research that I think holds a lot of potential is the development of what are called reasoning monitors. And these monitors will kind of act as an internal watchdog, analyzing that model's thought process in real time and flagging any of those potential vulnerabilities they could detect when the model is getting trapped in those unproductive reasoning loops or exhibiting any pattern suggestive of manipulation by attacks like, the think less attack.
So that's kind of like giving the LLM a built-in security system
Hmm.
that can recognize and alert us to suspicious activity within its own thought process.
Exactly. Another promising approach is incorporating what are called meta-reasoning techniques. And this involves training the model, not only to solve the task at hand, but also to reflect on its own reasoning process and identify any potential flaws or biases and adjust its approach accordingly.
Oh, so we're essentially teaching the model to be more self-aware
Yeah.
and critical of its own thinking. It's like encouraging a healthy dose of skepticism within the LLM itself.
Exactly. By fostering this metacognitive ability, we might be able to create models that are more resilient to manipulation and less likely to fall prey to those cleverly designed adversarial traps. They would be equipped to question their own assumptions, recognize those potential biases, and kind of, double-check their reasoning before arriving at a conclusion.
These are all really fascinating avenues for future research, and they kind of underscore that need for a multidisciplinary approach to AI safety. It's not just a challenge for computer scientists. We need cognitive scientists, ethicists, many other disciplines, working together to ensure that these really powerful technologies are developed and deployed responsibly.
I completely agree. AI safety is a really complex challenge that demands a collaborative effort from diverse fields of expertise. Open communication and collaboration between researchers, developers, and even policymakers will be crucial to navigating this evolving landscape of AI safety and ensuring that these powerful technologies are actually used for good.
Well, our deep dive into training inference-time compute for adversarial robustness has really revealed both the promise and the complexities of securing these LLMs. And while increasing inference time is a really valuable tool for enhancing those defenses, it's clear that we need that comprehensive approach that addresses the subtle and multifaceted ways in which these models can be manipulated. And this research reminds us that AI safety is an ongoing journey, and staying ahead of those potential threats requires continuous exploration, innovation, and that commitment to responsible AI development.
That's a great summary of the key takeaways from this research. As LLMs become more integrated into our lives, understanding these security challenges and developing those robust solutions will be essential to ensuring their safe and beneficial use. And this paper serves as a really valuable contribution to the field, sparking those important conversations and pushing us to think critically about how we build and deploy these powerful technologies.
Well, thank you so much for joining us on this deep dive. We hope that this discussion has really shed some light on the challenges and the opportunities in the realm of AI safety, and hopefully inspired further exploration of this crucial topic. Until next time, keep learning, keep questioning, and keep pushing those boundaries of responsible AI development.